Hi, this is Dr. Rajkumar. I'm a laparoscopic bariatric surgeon affiliated to Lifeline Hospital in India and the Burjeel Hospital in the United Arab Emirates. Let's now talk about the risk of liver fibrosis progression from the fatty liver in obesity vis-a-vis alcohol-induced progression of liver disease. So, non-alcoholic fatty liver disease, which is not as well defined as alcoholic fatty liver. While hepatic steatosis can be viewed simplistically as an imbalance between the process of lipid accumulation and lipid disposal inside the liver, the cellular and the molecular regulation of hepatic metabolism is intricate and has been the subject of recent extensive review. Fat in the liver is acquired from the diet via lipoproteins by de novo lipogenesis, by circulating non-essential fatty acids or NEFA, and is removed through VLDL secretion or by beta oxidation of the fatty acids. Derangements in each of these pathways have been associated with NAFLD. Traditionally, it was considered that fat accumulation in the liver occurs in the context of obesity and peripheral accumulation because of peripheral insulin resistance, with lipid coming from an elevated plasma non-essential fatty acid or NEFA pool caused by increased activity of hormone-sensitive lipase and increased lipolysis from engorged adipocytes. Multiple lines of evidence suggest that this straightforward explanation seems to be a bit too naive. Indeed, it has been postulated that systemic insulin resistance might itself be secondary to the NAFLD. Once steatosis is established, multiple mechanisms contribute to lipid-induced further cellular injury. Increased mitochondrial beta oxidation of NEFA leads to an increase in reactive oxygen species. Mitochondrial defects have been observed in patients with NAFLD, and impairment of the respiratory chain also produces reactive oxygen species and leads to extra mitochondrial NEFA oxidation in the peroxisomes and in the macrosomes, producing further reactive oxygen species. The overall increase in oxidative stress inside the liver leads to lipid peroxidation, damaged DNA, protein damage, and ultimately cell death. In addition, the aldehyde byproducts of lipid peroxidation increase production of pro-inflammatory cytokines within the liver, and they recruit newer inflammatory cells into this area. Inflammation and the activation of hepatic stellate cells leads to collagen production, and ultimately this initiates the process of hepatic fibrosis. Now, let's study what happens. We've looked at NAFLD without alcohol. Let's look at what happens when obesity and alcohol get together. This is a deadly duo. Alcoholic dehydrogenase is a hepatocyte cytosolic enzyme that converts alcohol to acetaldehyde. This acetaldehyde is further reduced and metabolized to acetate via the mitochondrial enzyme known as acetaldehyde dehydrogenase. So there are two dehydrogenases. Both steps are coupled to the reduction of NAD to NADH. So by the time alcohol becomes acetate inside the liver, there is an increased NADH to NAD ratio because of the double dehydrogenation. This has profound effects on the metabolism of carbohydrates and lipids. Gluconeogenesis is impaired and substrate flow through the citric acid cycle is diminished. So the acetyl coenzyme A, instead of going into the citric acid cycle, gets diverted towards ketogenesis and fatty acid synthesis. Together with the inhibition of mitochondrial fatty acid beta oxidation, the latter effect of the altered redox state contributes to the pathogenesis of a fatty liver or steatosis. So the total amount of fat in the liver is dependent on how much of oxidation happens vis-a-vis how much of deposit or synthesis happens. The pathogenesis of alcoholic fatty liver is based upon the combination of an increased glycerolipid synthesis and a decreased fatty acid oxidation in mitochondria. In addition to synthesis and oxidation, fatty acid export processes also influence the fat levels. In summary, ethanol metabolism leads to excessive generation of lipid inside the liver with a decreased oxidation of the available fatty acids inside the liver. In addition to the increased synthesis, we now know that there are multiple other factors that stimulate lipogenesis inside the liver. For example, we know that alcohol acts upon AMP kinase, which is adenosine monophosphate kinase, and inhibits its activity. Inhibition of AMPK causes an upregulation or increase in another enzyme, a transcription factor called SREBP1 or steroid-related endoplasmic protein receptor 1. When there is an upregulation of genes in relation to an SREBP1, there is a huge increase in fatty acid synthesis. At the same time, the inhibition of the adenosine monophosphate kinase also affects the activity of a peroxisome receptor known as a PPAR alpha or plasma peroxisome activated receptor alpha. Reduced PPAR alpha activity will also lead to a reduced capacity for fatty acid oxidation. In addition to fatty acid synthesis and oxidation, ethanol also alters the LDs or the triglyceride storage form metabolism in the hepatocyte and inhibits the secretion of very low density lipoprotein or VLDL from the liver. All these together, preventing the VLDL excretion, preventing fatty acid oxidation, and increasing synthesis of fatty acid, all these help us to understand the intricacies of ethanol-induced liver damage.